All right, let's go ahead and get started. Since today we're just doing exam review, I know the monitor isn't on. I went ahead and hit record, so at the very least the audio would be recorded, and I'll go through the slides kind of on the board, so you'll see what's on them. So yeah, this is a little weird with the screen not being on, but we'll just sort of run with it. So this is the exam review day, so you all have a celebration on Wednesday. So first off, if you haven't already done so, I need your homework number 7, because it's due today. I got a pile of them up there. Now, let's see. So I wanted to just go through, I'll go ahead and put this stuff on the board because it's kind of important in terms of scheduling. So we have 2 remaining homework assignments this semester. So we have homework 8, which is on development length. It's due on April 24th, which is a Wednesday. And it's assigned on the 17th, the Wednesday prior. This is probably the easiest homework assignment we'll have this entire semester, is the one on development length. I would say if there's any assignment that was comparable in difficulty, I don't know if you remember assignment number 3, where all we did was just the ACI requirements, the fee, and the strain checks. I'd almost say that one's a little tougher, because you actually had to look at the strain and make a decision or something. Development length is a really, really easy concept in this class. It's pretty straightforward. Homework number 9 isn't too bad. It's on columns and beam columns, and it's due on May 3rd, and that's a Friday, because that's our last Friday. That's our last lecture. So, well, don't be too happy about the class ending. I mean, come on. You're like, Dr. Mike, you've been putting us through hell for the past few years. It isn't that bad. Okay. This is really awkward with the monitor not being on, but oh well. Any questions though about this? This is it for this semester. For steel design, for those of you that are in steel design, which is the vast majority of you, we have 3 homework assignments remaining in the semester. One of them you've got now, which is the homework 7, which is columns and frames. Then you'll have homework 8, which is on continuously braced beams, and homework 9, which is on discretely braced beams. But it's a similar schedule. So yeah. Okay. All right, with that, let's talk a little bit about the exam. And I'm just going to do this on the board. I'm not putting anything on the board that isn't on the slides. And so, I mean, everything's on Blackboard. Okay, so first off, y'all know the drill in terms of, the exam format. It's really not going to be any different than it has been in previous instances. We're going to start the exam at 9:55 if everybody's here. So come early, and we'll start early. Let's see. So I'll have a scratch paper. I'll have. Oh well. Okay. Now the monitor decides to come on. Okay. I didn't do anything. I just was walking around and. Okay. Don't touch it. Don't touch anything. Okay. All right. I'm not touching anything. Of course. I swear, if I turn the lights on and then the monitor comes on, I'm going to be upset. Okay. That's one thing. I mean, it dangled this carrot of hope in front of me just to yank it away. You're like, it's funny, Dr. Mike, that's a lot how an engineering degree feels like. I love this job. Okay, so in terms of the exam content, it's going to cover lecture notes 10 to 11, and homeworks 6 to 7. So again, and I know I've said this a number of times, but I want to be clear on it. Homework number 5 is not on the exam, okay? Homework number 5 is not on the exam, and lecture note 9 is not on the exam. And so that's T-beams and doubly reinforced beams and the accompanying homework assignment. That's not on the exam, okay? I'll provide scratch paper. I'll provide staplers, although I'm probably going to do it like I did previous exams, give you a room to write on that little packet of scratch paper. Also, if there's anything that's tabulated that you need, I'll provide. So you don't have to start recreating rebar tables and anything like that. Okay. Let's talk about concepts. So really what we're talking about is 2 primary concepts. So we're talking about shear and deflections. So let's talk about shear. Shear and deflections. Okay. So for shear, I have 4 bullet points. I have mechanics, understand the mechanics. Be able to compute capacity. I have we're not touching the lights. The monitor's on. We're not touching the lights. So deal with the glare. God. I didn't even do anything. That's the crazy thing. The monitor comes back on. Okay, so be able to generally describe the mechanics of shear, be able to compute the capacity of beams in shear. I need you to be able to construct shear diagrams. That's kind of a big thing for shear, is being able to properly construct those shear diagrams and identify the 3 regions of interest. And those 3 regions of interest are when you need reinforcement for capacity, when the concrete can carry the shear by itself, but you still need to provide reinforcement, and lightly loaded areas where you don't need any reinforcement at all. And so you all should understand how to identify those regions. Be able to determine required stirrup spacing and layout, so layout shear design. Serviceability requirements, be able to identify the reasons for serviceability requirements. Why do we care about deflections? A big one is being able to compute an effective moment of inertia, and so that means you also need to know how to compute the cracking moment. You need to know how to compute the gross moment of inertia and the cracked moment of inertia. And finally, be able to compute deflections based on instantaneous effects and long-term effects. I've got some formulas for you in this packet, so let's start off with shear. So the shear capacity has to be greater than or equal to the shear load. Shear capacity is defined as the summation of the capacity generated by the concrete and the capacity generated by your steel reinforcement. Remember, for shear, phi is always 0.75. The capacity provided by the concrete is computed as 2 lambda times BD square root of FC prime. And the capacity generated by the shear, or by the steel, is the area of shear reinforcement times your yield stress times the number of stirrups per beam depth, so D over S. As for the regions, here's the 3 regions of the shear diagram. Anytime that the shear is larger than phi VC, anytime it's smaller than half of phi VC, and the middle region, which is the region in between. As for the design formulas, I really only have 3. 2 of them are focused around determining the absolute maximum spacing that you can use. And the monitor cut off again. Now, come on. I wasn't anywhere near the computer. This one isn't me. There's a poltergeist in the machine or something. Okay. Okay, I'll just stand here. So as I was saying, I have 3 formulas related to reinforcement. 2 of them are in order to determine the absolute maximum spacing that you can use. Notice that those formulas are completely independent of the load and anything like that. That's just the absolute maximum spacing that we can use. But then there's S required, which is within a given region, what is the required stirrup spacing in order to adequately resist loads. As for deflections, the big one, or at least the one that's new from structural analysis, is the effective moment of inertia. So the effective moment of inertia is essentially a weighted sum. You know, it's a little bit of the gross moment of inertia and it's a little bit of the crack moment of inertia. And that little bit, quote unquote, is for the gross moment of inertia, it's the ratio of the cracking moment and the applied moment cubed. And for the crack moment of inertia, it's 1 minus that ratio cubed. Now, remember, when you're doing serviceability, what do you not apply when you're checking deflections? Say it again. You don't apply your load factors. Exactly. You're just using service loads. Oh, man. I didn't even do anything. I was like, now this one, I was on the other side of the room. So yeah. I don't know what's up. Okay. So, all right. Back to effective moments of inertia. So the first thing is you don't apply load factors. The second is you cannot compute live load deflections directly. You can compute a dead load deflection and then a dead plus live load deflection, and then you can take the difference, and then same thing with the sustained live load. As for long-term effects, you're taking your instantaneous effects and adjusting them by a modification factor. That modification factor is a function of two things. It's the reinforcement ratio of compression steel. If you have it, I'm just going to, we're just going to do it live. The reinforcement ratio if you have compression steel, and then a time-dependent factor. The time-dependent factor is that curve, the one that sort of looks like this. You have your time and then your curve, and it sort of goes like that, and you just have to find a value and go over. What's the absolute largest time-dependent factor you can have? 2, which is why for dead load effects, when you compute total deflection, you take the instantaneous live load deflection, you take the sustained live load modified by whatever its duration is, and then you take the dead load modified for an infinite duration. And the only difference between a duration factor or a duration modification and an infinite modification is that your time-dependent factor is always 2, because you can see how the graph, it's pretty asymptotic when you get close to 2. And that's basically it. That's your second exam. So with that, I am going to shut up and let you all ask whatever questions you want. Floor is yours. Yes, sir.
Conceptually, why can't we solve for just the live deflection?
Okay, so the question was, why can't we solve for the live load deflection directly? Well, there's a short answer and a long answer. The short answer is because when we compute an effective moment of inertia, it's a nonlinear problem. So you can't, it's not like it was in structural analysis. In structural analysis, we could do that. In 312, we could do that. We could say, well, what's the deflection due to 10 kips? Well, then what's the deflection due to 50 kips? Well, it's just 5 times that, or you can just say it's the deflection due to 10 kips plus the deflection due to 40. And the reason we could do that is because it was linear. It was just a scaled factor. But that's not the case. I mean, your moment of inertia is, that ratio cubed plus 1 minus that ratio cubed. There's a nonlinear effect to it. That's the short answer. The long answer is if you have a beam, here's the supports, and you have a beam. I'll do a little bit of a better job than that. So here's the beam, and it's sort of sitting on these supports, okay? So the first thing that the beam experiences is its own self-weight, okay? So under its own self-weight, especially if that moment exceeds the cracking moment, you're going to get a little bit of cracking, right? So if you want to think of that analysis, you can think of that analysis with a beam that looks like this. Actually, hold on. And so it sort of goes maybe like that. And so that's your weighted moment of inertia under dead load. But then you say, okay, the next thing I'm going to do is I'm going to stack a live load on top of it. Okay, and that's going to cause even more cracking. And that cracking is going to propagate, along the span. Okay? So under dead load plus live load, you actually have a different, it's a completely different beam. Okay? So I guess my question is, which beam would you use if you wanted to compute live load deflection directly? Would you use this one or would you use this one? And the dead load. That's the problem. It has this cracking and this beam is caused by dead load plus live load, not the live load by itself. Okay? So how much would you consider? I don't know. And the reason I don't know is because the moment of inertia, it's not linear. Remember, you're taking, you've got that effective moment of inertia. You're taking that ratio cubed plus, 1 minus that ratio cubed. So it's not a straight line. So that right there makes this incredibly difficult. And that's why you can't do that. Did that make sense? Everybody else, did that make sense? Okay. All right. This is your time, so. Yes?
When you're calculating rho prime.
Rho prime.
I know it's AS prime.
That's a good question, and that's a very easy area of mistake, and the answer is it's D. Okay, so rho prime is AS prime, but it's BWD. And the reason why is because this right here is still basically the area of the concrete. Here's a beam, right? And, here's your AS, here's your AS prime, okay? Now let me ask you a question. In general, without looking at any formulas, any equations, take the math and eliminate that. Which do you think should be bigger, rho or rho prime? What's that? I mean, think about what rho is. Rho is a reinforcement ratio. It tells you a percentage of how much reinforcement's in the beam. What I'm asking is this. Generally for a beam, are you providing more tensile reinforcement or more compressive reinforcement? You're providing more tensile reinforcement. So really what should happen is that should always be bigger. Okay? And so the way that we handle that mathematically is we say that rho is AS over BWD, and this is AS prime over BWD. Well, that might not happen if we use D prime. Okay? Think about what the beam looks like. Okay? Let me erase this over here. Okay, so I've got two beams drawn side by side. This is the exact same beam. Okay? B times D, that's essentially going to be this area, which for the most part is the effective area of the beam. Remember, we really don't care about that little sliver of concrete down below. When we compute our moment capacity, it's a function of D, not H. Whereas BWD prime, that would be just this area. Well, if rho is supposed to be a percentage of how much steel is in the beam, it really wouldn't be representative if we were using D here and D prime here. We could actually get a larger value for rho prime. And so the way that we do that is we just use a common denominator. We want that denominator and that denominator to be the same. So that's how we handle that, is we use the same denominator but a different numerator. And the numerator is AS if you're looking at tensile reinforcement and AS prime if you're looking at compressive reinforcement. But we use the same denominator. Does that make sense? That's sort of the way that I memorize that, is I just think, well, I'm trying to look at just how much steel versus how much concrete. And so realistically, if I'm trying to look at how much concrete, I'm looking at all the concrete. Does that sound good? Any other questions? This is your time. Yes?
This delta long-term equation.
Yes.
What is the difference between it and the delta total, I guess? Like, why do we need?
Oh, that's a good question. So I'm going to erase this. So the first equation that you're referencing is that, that long term. And basically what that's saying is you have some modifier times an immediate effect, right? Okay, so if you want, you can think this is just sort of a conceptual basis for the second formula. So you could use this formula and say, okay, my delta, sustained live load is going to be, lambda times the duration times, that. I guess I should say, long term, right? And then my dead long term is going to be lambda times infinity because it's an infinite duration times that. And so I'm using this expression right here to generate this one.
Why do we not do the delta live divided by delta lambda?
That's a good question. Okay, so let me answer that. I'm going to answer that by sort of writing it out. Okay. Sound good? Okay. All right, so the question was, why is this not modified? Like, why don't we have a modification factor here? The answer goes back to the Dunder-Mifflin Paper Company example that we mentioned earlier. Okay? So at the Dunder-Mifflin Paper Company or at some general structure, okay, live load is transient. It goes in and out. Okay? Take this classroom, all right? At 11 o'clock, I'm going to have a whole different group of people in here. And at 12 o'clock, there's going to be a whole other different group of people, right? But what is sustained in this room? Like what? Let's just characterize it. In this room, what's the sustained live load? The desks, the tables, the chairs, that station, the whiteboard, this TV that doesn't seem to want to work. That's the sustained live load. Whereas the full live load is essentially all that, plus the occupancy. Now, what we're trying to do is determine a total deflection plus that long-term effect. So if you want, you can think about it like this. This part right here, that part right there is the deflection once that load is applied. But this right here, this is the deflection that's affected by long-term. And so I guess the better answer to your question is if 100% of that live load was sustained, if all of it was sustained, then we would have the instantaneous effect and then the long-term effect, and that would just be delta L as well. Or another way you could write it is that deflection total would equal, that plus, and then basically that, if 100% of that live load was sustained. And if none of it was sustained, then just remove that. Like, what if it was a structure where load was literally coming? What if it was a structure where none of it was sustained? Well, then that part would just go away, and you would just have the instantaneous effects plus the long-term effects of the dead load. So the theoretical answer is the long-term effects. The difference is how much of that load is sustained. Good questions. It's your time. Yes?
So if you ask us a question like number 2 on our homework page,
Mm-hmm.
wanting to get this delta total, that's pretty long.
Mm-hmm. I know.
Would you give us like the beginning values or something?
That's a good question. I'll say this. I'm not going to tell you what I'll give you and what I won't give you, but I'm going to say 2 things. Okay? Number 1, and maybe your faith is shaken in me after the steel exam, but I do still apply a rule of 3.
I've already heard about this last test.
What's that?
I already heard about this last test
What?
for concrete.
What?
Everybody said the finals you had a cantilever beam on there, and they were
Well, that was last year.
I know. There's going to be another curveball this year.
Well, that I can't get around that. You know.
Straight slobbers down the center.
Well, hold on. Okay, so I have a couple responses to his question, but the response to your question is, sorry, couldn't help it. But let me be serious, okay? I do understand that. I do, and I do try and do that to ensure that it's not a time crunch. I don't think that that's an effective use of time. So I will do my best to work around that. But there is a flip side, okay? And the flip side is you've got to read the problem, okay? I've given exams like this before, and I'll hear people complain about time, and then I look at their work, and they sat here and computed the whole thing. Whereas if they had read the problem, they would have only needed to do a third of that work, you know, because there might have been some values that were given to them. So it's a trade-off, you know. Like, I can help you out with time, but that means you've got to read. That's the trade-off. So pay attention is I guess what I would say. Because that's happened. I mean, and I'll go into. It's probably going to happen on this exam as well. Even if I do give you data that will reduce the length of the problem, there will be people who go, well, this is what we did in class. This is how I studied it. This is what I'm going to do, and it's going to take way more, much more time. So, but if you actually just understand the concepts, it'll go a lot faster. So, yes.
Other than just like simple math errors or not reading the problem, are there like any common mistakes that you see on this particular type of exam?
That's a good question. So I'll repeat it for the recording. The question was, other than like math errors and not reading the problem, are there common errors that show up? Yes. And I would say that the most common error is making the problems more complicated than they really are. That one right there, especially for this exam.
Specific type of problem that stands out?
Yeah.
Would you like to share?
No.
Give you
That was good. That was good. But this is what I will say. All right. Of all of the exams in steel design and concrete design, I'd argue this one's probably the most heavily reliant on just your basic understanding of structural analysis. You have to construct shear diagrams. You have to, you have to do that, And you didn't really have to do that on the first exam. You could just either use WL squared over 8 or whatever, structural analysis formula made sense and you were good. Well, you kind of need to. I give up. I give up on the monitor. It's just turning on and off. It's just doing whatever it wants. But this one requires you to understand, what does a shear diagram look like? If I have this set of loading, what is the shear diagram going to represent? And so that part, I think, matters the most. Yeah, that would be my answer. But yeah, if you understand the fundamentals of the math and the fundamentals of the what the problem is stating, you should be fine. But read the problem. Yes. MA.
Yes, MA. Okay. So if I have like a distributed dead load, then like a point live load.
Mm-hmm.
So do I use two different equations?
Yes.
And then I get and then the same thing for like the deflection.
Yes. Yes. So I'll give you a basic example. Can I erase this? All right. And I'm only using these ones because they're easy to remember, like the formulas. So don't take any of this to the bank. But if you have let's say here's a structure. And for the sake of discussion, we have a dead load, and then we have a live load. Okay? First off, if you try and do this, hold on. I'm gonna be accurate about this because I got time. So if you try and say, okay, here's my dead load, and then my live load, I'm just going to take the point load and divide it by the length. If you try and do that, that's wrong, okay? And the reason that's wrong is because if all I'm doing is looking at the point load, like let's walk this through because I think y'all need to see this, okay? Let's come up with some simple numbers. All right, let's say this is 10 feet and this is 10 feet, and let's make this 40 kips. Let's go back to 312. What are the reactions? Are we all good on that? Okay, so the beam's 20 foot long, right? Okay, now, the beam's 20 foot long, right? 40 kips. So this is what you're wanting to do, right? You're wanting to do that. Turn it into a distributed load. Okay? Again, 20 foot long. What are the reactions? $20 kips. And I'm sure you're sitting here saying, but Dr. Mike, you're not really making a lot of sense. I thought you said we couldn't do that. The reactions are the same. Well, I'm not done. Let's draw the shear diagram. What's the shear diagram look like over here? Tell me what to do. Up 20, over, down 40. So if this is in kips, that's my 0 line. This is plus 20. That's minus 20, right? Okay. What are the areas inside there? What's the area inside here? So tell me what the moment diagram looks like. Straight line up to 200, straight line down, right? So up, down. And so this is 200, 0, and 0. So for here, let's erase this. So for here, M max is 200, right? Now what's the formula for this case? It's M equals PL over 4, right? So that's what? 40 kips, 20 foot, divided by 4, and what does that come out to be? 40 divided by 4 is 10 times 20, 200 foot kips. Craziness, isn't it? Right? Okay, what about over here? What's your shear diagram look like? Go up 20. To minus 20. Back up, right? What's the area of that triangle? First off, what's this distance? 10. So what's the area under that triangle? 100. 20 times 10 divided by 2. Lot to a little, little to a lot. Twenty squared is 400, divided by 8 is 50, times 2 is 100. Okay? So here's the thing with this collapsing the load into a point load or spreading it out into a distributed load. It works for static equivalency when you're trying to determine the response at a point. Okay? In other words, when you're trying to determine a reaction is a response at a particular point. So statics doesn't really care about this and this. But shear diagrams and moment diagrams aren't about response at a particular point. They're about distributed responses over the whole diagram. You're plotting the response across the whole beam. Okay? So it's not the same story. Okay? If you know, think, if I have this beam, okay, I mean, let's just use some common sense. Here's a beam. I'm actually glad I brought this today. Here's a beam. Between two supports. Okay? What's the worst case scenario? If I lump that load all in the middle or I spread it out? What's the worst case scenario? Lumping it in the middle. So when you say, well, I'll just take this point load and turn it into a distributed load, that's incredibly wrong and incredibly unsafe. Okay? You can't do that. Okay? That's fine for support reactions. The geotech engineer doesn't care. Okay? But the structural engineer is going to look at that and see, well, oh my goodness, you have drastically changed what's going on. Okay? All right? Does that make sense? All right? And another thing, I don't want you to think that these formulas, these WL squareds over 8s are anything crazy. I mean, they're nothing magical. I mean, like, look. So, I mean, if you have a point load, P, and this is L over 2, and this is L over 2, then that reaction is P over 2, and that reaction is P over 2. Would that be a fair statement? That would be a fair statement? So what does the shear diagram look like? You go up P over 2, go down to minus P over 2, and go over. So that's minus P over 2, that's P over 2, and that distance is L over 2. So what's the area of that box? It's P over 2, or it's L over 2 times P over 2, or PL over 4, minus PL over 4. So what's your moment diagram look like? Go up to PL over 4, go down PL over 4. Right? So that's where these formulas come from. I don't want you to think that they're anything magical, because they're really not. You know, it's just doing this with letters instead of numbers. Okay? So does this make sense? Okay. So let's go back to your specific question and go back to the example that we were looking at. And then we might have to call it here. We'll see. So a dead load and a live load, right? And we'll say everything's symmetric, so I have no worry about that. So we have the dead load case. So we're going to have an MA, right? Which is in turn going to produce an IE, which is in turn going to produce a dead load deflection, which is 5 L to the 4 over 384 EI. Then our dead plus live load case is going to produce a different moment. And if you try and turn that into, or turn that point load into a distributed load, that's wrong. Okay? You're going to have this plus that. Okay? You're going to add those moments up together to produce that, to produce this. because this is the formula for a simply supported beam with a point load in the middle. It's PL cubed over 40 ADI.
Obviously, there's a lot of these in the spec window from Blackboard. If you give us anything else, you give us some off the wall.
The ones that you need. The ones that you need. You don't have to re-appropriate that on your homework or on your formula sheet. Does this make sense? And look, don't take this case to the bank. I mean, I almost guarantee I'm not doing that case on the exam since we talked about it in here, you know. But does that make sense? So turning this point load into an equivalent distributed load is fine when you're determining reactions at a single point. See, one of the things that we used to do in structural analysis is we would take a beam like this and we would samurai sword or lightsaber through it, and we would have something that looks like this. We'd have, you know, a reaction, and then we'd have this, and we'd have that, and then we'd say, okay, we've sliced it right here, so there's a shear, and there's a moment, and then we would take this distributed load, and we would collapse it into some point load, if you remember that, right? But two things. One, that would always be a function of x, like it'd always be a function of some distance. And two, we were always just trying to determine the moment at x, or the shear at x. In other words, what's the moment right there? What's the shear right there? That process of collapsing a load into a single point load, or vice versa, is fine when you're trying to determine the response at a single point. As soon as you try and determine distributed responses, like a shear diagram or a moment diagram, that goes out the door, okay? And you don't have to believe me, just look at this. You know, these two loads are statically equivalent in terms of the reactions, but the response is way off from then on, way off. Yes?
When we calculate the moment applied, and we get the actual number and compare it to the cracking moment, and it's actually less cracking moment, we should use the gross.
Yes, that's a great question. And the short answer is yes. If you have a beam that doesn't have any load on it at all, like very lightly loaded, so if you have a cracking moment of, let's say, 40 foot kips, and your applied moment is only 10 foot kips, just use IG, don't use IE, because the beam isn't cracked. Great question. Answer is yes. Use just IG. All right. We got plenty of time for, well, by plenty of time, that means we got 4 minutes. So. But this is a good review session. I really like this. This is some good stuff to walk through. Any questions? Yes. Yes, and some conceptual problems.
Okay, so if we could run down the two topics, I think that the question would be more geared towards the one that has two problems towards it, like
Maybe.
live load and total, or not live load, like function and total.
Maybe, or I give you 2 shear problems. Here I am throwing stuff around. Yeah, I was thinking about throwing a fluids problem on there. Yeah.
So could you really get that CO exam done in 20 minutes?
Yeah. I got it done in less than that.
My problem is I started writing on the formulas before I put numbers in it, and then I got towards the end I'm like, crap. So I just write numbers.
Well, but the second problem, the bolt problem, the second one, like you just look up most of that. Those were all lookups. Other than the bolt bearing one you had to work out. But bolt slip and bolt shear, those were lookups. And that's what we did in class. We did look them up. No. I told y'all that the senior design came first. That didn't happen. So. All right, we got 2 more minutes. Any other big ticket questions? Well, then that's all I have, everybody. I'll see you all in... Oh, one final thing. Don't forget, on Friday, we have that professor coming in. Just so if you're wondering, who's that? So they're just going to be hanging out with us. So. That's all I got. I'll see you all at 11 or Wednesday. I'm shutting down and restarting this computer. I hope that helps.